Finding the time given an exponential function with base e that models a real-world situation. The number of bacteria, P of H, in a certain population increases according to the following function, where time, H, is measured in hours. P of H is equal to 1,900 times base e raised to the 1800ths times H. How many hours will it take for the number of bacteria to reach 2,600? Round your answer to the nearest tenth, and do not round any intermediate computations. Remember, E is actually about 2.718, so that number is more than 1. That means this model is actually exponential growth. Why don't we sketch this really quick? At time 0, how much bacteria is there? When H is 0 hours, how much bacteria is there? You can easily see that when H is 0, so here's H, here's the P of H axis. And when H is 0, we know that this is already at 1900. And now we do know it's exponential growth. So we're going to draw a dotted line on quadrant 2, but then it becomes a solid line in quadrant 1. The question that we want to answer, I should say, is when do we reach 2,600? So what are we really trying to find? We're really trying to find some kind of H value. We could call it H down here. I don't like how I labeled that. Why don't I fix that really quick? And it's some H value here. You could call it H sub star if you want. But we're trying to find that H value. Well, we know P of H. We know P of H is 2,600 at that time. So if we substitute 2,600 equals 1,900, then this becomes an equation that you're much more familiar with. And now we divide the entire sides by 1,900 because 1,900 is not 0, and we have 26 over 19 is equal to base e raised to the 1800th times h. Now we use the natural log function, which is the inverse function of the exponential function. That's how we're going to get h. We take the natural log of this side, and the input is 26 over 19. We take the natural log of the right-hand side, and the input is e raised to the 1800ths times h. Now we have log properties. The log properties say that this is 1800ths times h is now equal to the natural log of 26 over 19. We could divide the entire sides by 1800ths. And what do we get? We get h is equal to 50 over 9 times the natural log of 26 over 19. If you're wondering how did I do that, remember divide by 1800ths means really multiply by 100 over 18. So that's what I did in my head. I guess I could draw in my head. There's my head. I'm going to go ahead and circle that exact answer. So in mathematics, especially in algebra, we want to find the exact answer first before we actually round any computations. Remember your units. make sure you put your units here. This isn't decades. We want to make sure we label hours. So make sure you write that on your paper. Now, let's find a decimal approximation. Typically, you get your scientific calculator, and you're going to type the natural log of 26 over 19 first. I'm going to go ahead and hit enter. Then I'm going to multiply it by 50. And then I'm going to divide by 9. And we get this number here. H has this decimal representation. 1.742541994 ... because it never stops. It doesn't terminate. It does say round your answer to the nearest tenth. So we're going to look at the hundredths place. 4 is less than 5, so we're going to round this down to 1 7/10. Now, if the problem is given to you in words and sentences, you probably should answer it back in words and sentences. Maybe actually one sentence is often enough. It will take about 1.7 hours for the population to increase to 2,600. Now ask yourself, does that make sense? Does it make sense with all the graphs that you've been graphing throughout your algebra career? Why don't we take a quick look? Is the model increasing? And is the time, appropriate? I would say so. It's not, completely bogus that, it would be really, really unusual if you got an extremely large number here. If this said 2,000 hours, well, that doesn't really represent exponential growth, because exponential growth should happen rather quickly. So the answer makes sense. Why don't we circle it?